We're finishing up chapter 14 today. I just want to mention this quickly because our book mentions it, and just so that you realize, we've talked about probability being based on something in the long run. But if you base your probability on some personal assessment without actually basing it on something that's happened in the long run, then you're using a personal probability and you're not actually using an actual probability. All right, so personal probabilities may be based on experience, but they're not based on long-run relative frequencies or equally likely events. So they don't show any sort of consistency. So personal probability might be that, okay, in the past you haven't done so great in English class, and so you say that you don't think you have a very high % chance of doing well on the test. That's based on personal experience. That's not based on an equally likely event in the long run. So just be careful of that. If you run into anything on the homework that's asking you to comment on anything, or if you run into questions, just make sure your probabilities are actually based on factual, long-run frequencies, okay? All right, so we're going to be calculating probabilities today, and you are very familiar with the things I'm going to tell you, so I won't stay on them for very long. I understand that you know them. What we need to make sure we know is the notation. So capital P is always going to denote probability in this class. So we generally have the probability of some event in the parentheses. So here we have the probability of A. And we know that's equal to the number of outcomes that are A over the number of total possible outcomes. So for example, the probability that you get a face card from a deck of cards, you take the number of face cards and divide by the number of cards, and you get 3 over 13. Yes, I would like for you to use the notation and write this out. I know that seems annoying, but on the AP exam and on tests in this class, if you, for some reason, make a mathematical mistake when you're typing something in your calculator and you just write down the answer, I'm going to count it wrong. But if you have written out what you're trying to achieve and maybe wrote out the work, then you'll probably get it right. Right? I'm not going to take off points if you showed all the work and then I can tell that you just typed something in wrong. So I'd like for you to use the correct notation. Also in this class, I know that often we write probabilities as fractions, but we use percentages and decimals in AP statistics because normally we're trying to use them for something else, right? So fraction form is fine, but it's just not what's standard in here in this class, okay? Our book, of course, loves for you to make pictures, and you can make pictures. We probably won't make as many pictures, though, until chapter 15. We're going to use some pictures for the rules in a second, but we'll use Venn diagrams and tree diagrams in chapter 15. We'll make tables in chapter 15. If you don't like doing that, you don't have to. This is just up to your personal preference. Again, we won't use this a lot in chapter 14, but just keep that in mind that sometimes a picture can help you figure out what's happening in the scenario. So there are 5 formal probability rules, and you know these, and we will talk about them, though, just to make sure everyone's on the same page. All right? The first one, if the probability is 0, then the event can't occur. If the probability is 1, it always occurs. So we also know that a probability has to be between 0 and 1. If it's not between 0 and 1, so if it's negative or over 1, then it's not a legitimate probability. All right? So legitimate probability has to be between 0 and 1. When you have all of your possible outcomes, they must all add up to be a probability of 1 or 100%. If the probability of the whole entire set doesn't equal 1, we have an issue. So does your probabilities add up to be 125%? That means there's overlap that we need to account for. All right? This is going to be a big thing we do in chapter 15. And also, just something to keep in mind in this chapter. The AP questions that we're talking about in this chapter aren't super complicated, but they might throw that at you where the probabilities don't add up to 100, so you need to keep track of that for the problem, okay? So just make sure you remember that everything has to add up to 100%. The next one is the complement. Suppose the probability that you get to class on time is 0.8. Then what's the probability that you don't get to class on time? is 0.2. Well, you did that by doing 1 minus 0.8 in your head, right? Well, that's what the complement is. The probability of an event occurring is 1 minus the probability that it doesn't occur. We're going to use it a lot. I can already predict what question you're going to miss on the quiz, if you miss any, because the questions aren't that complicated in Chapter 14, like I've said. And they're all the questions that say the probability that at least one of something happens. When we're talking about at least one, that's a lot of possibilities. That could be 1 or 2 or 3 or however many you're talking about. So instead of trying to do all that and making it very complex, you would just do 1 minus the probability of none of those happening. All right, so we'll be using the complement a lot today. So make sure you remember that one. Now, suppose the probability that A, a randomly selected student, is a sophomore is 0.2, and the probability that B, he or she is a junior, is 0.3. What is the probability that the student is either a sophomore or a junior? That's 0.5. And so that's where the addition rule comes into play. All right? If you have two disjoint or mutually exclusive events, which means they have no outcomes in common, this Venn diagram right there, then you can use the addition rule. When we're talking about juniors and sophomores, you cannot be a sophomore and a junior at the same time. Those are disjoint events. An M&M cannot be red and green at the same time. Those are disjoint events. So if you're talking about something or something else happening, then you're talking about something being disjoint, then you should be able to add those probabilities together. So if you have two disjoint events and you're looking for the probability of one or the other, not both, then you can just add those probabilities together. This notation right here just means the union. It's set notation, and it represents or. If you have one event or the other, you can add those two together. That's the addition rule. If the events are not disjoint, don't add them together. So it says, if the probability of owning an MP3 player is 0.5, and the probability of owning a computer is 0.9, then the probability of owning either an MP3 player or a computer may be pretty high, but it's not 1.4. You can't just add those together because they're not disjoint. You could own an MP3 player and a computer, so there is overlap. So you can only add these two entities together if there's no overlap, no outcomes in common, disjoint events. The last part is the multiplication rule. And the multiplication rule occurs for independent events. Right? Remember, independence means that one outcome doesn't affect or influence the outcome of another event or another trial. So, if you have two events that are independent, then you can multiply their probabilities. For example, let's say the probability of drawing a red M&M out of a big bag of M&Ms is 20%. Then the probability of drawing two red M&Ms in a row is 20% times 20%. Okay? You're just multiplying because they're two independent events. They're not disjoint, but you're looking for the intersection. So two independent events, that means and. You want something and something else to happen. Since you're looking for something and something else to happen, there has to be overlap that both of those happen together. Then you can multiply the probabilities. This symbol just means the intersection or and. And so we'll look at some examples. And if you have independent events, that means there's going to be some overlap, but the outcomes don't affect each other. Disjoint means there's no outcomes at all that are in common. All right? So events that are independent are not disjoint. Let's do some examples to make sure we understand these rules. I've got two sets of examples. All right. The first one are all the examples about the traffic light we've been talking about from yesterday. We opened the chapter by looking at the traffic light at the corner of College and Main. observing that when we arrive at the intersection, the light is green about 35% of the time. So if the probability of green is 35%, what's the probability the light isn't green when you get to College and Main? The probability of not green, again I'm using the notation, would be 1 minus 0.35, which is 0.65. So 65% of the time the light is not green. When you get to the light at College and Main, it's either red, green, or yellow. We know the probability of green is 0.35, and we find out the probability of yellow is 0.04. So what's the probability the light is red? The probability the light is red would be 1 minus the probability that it's green or yellow. So that's 1 minus 0.35 plus 0.04. They're disjoint. It can't be green and yellow at the same time. So that's 1 minus 0.39, which is 0.61. Again, yes, I do want you to use the notation. I know you could figure that out without writing it all out. We've determined the probability that we encounter a green light at the corner of College and Main is 0.35, a yellow light is 0.04, and a red light is 0.61. So let's think about your morning commute in the week ahead. What's the probability that you find the light red both Monday and Tuesday? The probability that the light is red on Monday and red on Tuesday. These aren't disjoints, you can't add them, but you have two independent days. You would think that one day doesn't influence the other. So we multiply, we use the multiplication rule. So the probability that it's red is 61%. So 61% chance it's red on one day and 61% chance that it's red the next day. We're just going to multiply those together. So 0.3721. What's the probability you don't encounter a red light until Wednesday? So that means it's not red Monday and not red Tuesday and red on Wednesday. We're just talking about a work week. So then the probability that it was not red was 0.39, if you remember from up here. And then it was not red again, and then it was red. So 0.0928. So again, these aren't disjoints, but they're independent events, so we can multiply the probabilities. And the last one, what's the probability that you'll have to stop at least once during the week? At least once. Stop means red. It's a work week, so that's 5 days. What's the probability of getting red at least once? Now this gets very complicated. At least once means it could be once a week, twice a week, 3 times a week, 4 times a week, 5 times a week, and it gets very complicated to come up with that probability. So instead, anytime you see at least once, you should do 1 minus the opposite. So instead of doing at least once, we can do the probability of, so 1 minus the probability of no red, because that's what's left over. Once or twice, 3 times, 4 times, 5 times are all possibilities for that probability, but you still have the probability of 0 red. So I can subtract that off, and I'm left with what would actually happen once, twice, 3 times, 4 times, 5 times. So I have 1 minus 9. That was the probability of it not being red for 5 days. So you could write 0.39 times 0.39 times 0.39, but we know we're multiplying, so we're going to write it to the 5th power. We get 0.991. That makes sense. It's 61% probability that you're going to get a red on any given day. And so the probability that you're going to get a red at least once should be fairly high. Be careful because some of the questions say some instead of at least one. That means the same thing. All right. This is the type of question that's going to be the most complicated, is when it says at least one. And we'll keep working on it. On the homework, there'll be plenty of examples. One more example, and I will give you the assignment. In 2001, Master Foods, the manufacturers of M&M's milk chocolate candies, decided to add another color to the standard color lineup of brown, yellow, red, orange, blue, and green. To decide which color to add, they surveyed people in nearly every country of the world and asked them to vote among purple, pink, and teal. And the global winner was purple. In the United States, 42% of those who voted said purple, 37% said teal, and only 19% said pink. But in Japan, the percentages were 38% pink, 36% teal, and only 16% purple. So let's use Japan's percentages to ask some questions. What's the probability that a Japanese M&M survey respondent selected at random preferred either pink or teal? Just using the Japanese percentages. And side note, this is why you got to be careful. If you add all these up, you only get 90%, so there's 10% missing. Just thought I'd throw that out there. So the probability that you get either pink or teal was the selection. Since we're looking for one or the other, we can add, because they can't be pink and teal. They can't choose pink and teal. So we get 0.38 plus 0.36. That should be 0.74. Not too bad. Question 2. If we pick 2 respondents at random, so now we have 2 people, what's the probability that they both said purple? So now we aren't doing one or the other, we're doing both. Probably they chose purple, and the next one chose purple. So since we have 2 independent events, we can multiply. So they chose 16% said purple twice. So 0.0256. And the last question, if we pick 3 respondents at random, what's the probability that at least one preferred purple? So again, it says at least one. That gets complicated. So we'll do 1 minus the probability that all 3 did not choose purple. So the probability of choosing purple is 0.16. And the probability of not choosing purple is 0.84. So we have 1 minus all 3 not choosing purple. We get 0.4073. That's the types of questions we're going to be answering in this chapter. Again, you can use the addition rule when things are disjoint. You can use the multiplication rule when things are independent. Be careful that you know those 2 vocabulary words. Make sure you know that disjoint is also mutually exclusive. The AP exam will use mutually exclusive, and our book's going to use disjoint. So be careful that you know that. All right? I will give you the assignment, and that way you have time to work in class, and you can ask questions.